And so next we have Andrea Urban, who will be talking about data science at an electric company.
Hi, thank you all for coming. I'm going to be speaking on like issue. So yeah, thanks for coming, and thanks to the organizers for organizing such a great conference and all the volunteers. It's really been fun. I've learned a lot already. So I'm Andrea Urban. I'm going to be talking about the work I do at Puget Sound Energy, detecting electric vehicles of our customers. Before I get started, just talk a little bit about Puget Sound Energy. So we're an electric company and a natural gas company. We're the oldest electric or energy company in the state and the largest. We serve most of western Washington, and we have 1.2 million customers in total. We have three different types of customers. We have electric customers over here in East Puget County and the Yellow and different regions. We also have natural gas customers in Seattle and Tacoma. And we have customers who use both electricity and natural gas for Puget Sound Energy. So this talk is going to be about detecting electric vehicles in our service area. So how many of you are Puget Sound Energy electric customers? Electric. How many own an EV? Okay, so you're my true positive. People are trying to detect. Everybody put their hand down, you're my true negative. I'm interested in you too, as like, they're not like, or EV customers, EV owners rather. So why do we want to detect electric vehicles in our service area? There's a lot of different reasons. Some of it is motivated by the Clean Energy Transformation Act, which was signed into law in 2019 by Governor Inslee. Basically, it says our electric supply in Washington State has to all come from greenhouse gas-free sources by 2045. So that's going to be changing our electric grid. In addition to, we don't just have to do this, we also have to make sure we consider equity in that. So, we could just build a bunch of solar power plants and increase everyone's rates, and people would be unhappy about that. So we have to do some other things to make sure we make this transition equitably. And some of the things we can do is provide incentives and rebates to some of our low-income or economically disadvantaged customers. And so that's part of this plan that we also have to consider. So we're also trying to reduce our greenhouse gas emissions, but also trying to make our customers, or help our customers be more energy efficient, like improve their appliances, improve their weatherization of their homes. So in addition to that, there was another law passed, which is basically saying that by 2035, all new vehicles that are sold in Washington State must be zero-emission vehicles. So that means there's going to be more EVs on the market, right? And these EVs need electricity to charge. And so because of this, PSC developed this transportation electrification plan, which you can find online. And in this, it shows that all the way up until at least 2050, most EV charging is expected to be in residential homes. So those are our customers, and we don't know who they are. So it's going to be a lot of energy being used to charge EVs. So we're interested in knowing who these customers are so we can help support our electric grid. So just a little background about how electricity works. This is about my level of understanding, just so you know. So like, we have a generating station, like a power plant, like a solar power plant, natural gas power plant. It's transmitted across these high voltage lines. Those are the big things you see out in the country, those big giant power lines. And then eventually, it goes into something called a step-down transformer, where the voltage is dropped down to a level that is good for your home. And so these are your customers who are the ones using energy. So these step-down transformers are responsible for making sure that the power that you get in your house is safe and stable. And so there's this information we have, some ideas we have about EV charging. It's unique on the transformer. It's not your standard type of energy usage. It looks a little bit different. It's typically a large load for a long period of time. And it's a continuous load, And but once you're done charging, it drops back down to normal levels and it's fine. But we have some ideas that that kind of load on our transformers can lead to degradation of our transformers a little bit sooner than we would expect. So we want to know where these EVs are so we can make sure we're monitoring those transformers and making sure we're able to replace them before they fail. So we do monitor the overloaded transformers, so we do know which transformers are overloaded, but it's also important for us to know which ones have EVs on them, because if a transformer has an EV on it and it's overloaded, there's this idea of like keeping up with the Joneses. If one transformer has an EV on it already, the neighbor might also is more likely to get EV, and then once that happens, the transformer is going to fail. So that's also why we're interested in knowing where these EVs are. So here's an article from the Department of Ecology, basically saying that it's a record year for electric vehicles. The growth is astounding, but also within that article, it's just 3% of the vehicles in the state. So it's a small number. Yeah, it's growing, but it's still a small number. And because of this, this is a highly imbalanced problem, right? We're looking for a needle in a haystack. There's not a lot of EV owners, but when they are, we're worried about them. So that's what we're looking for. And so that's like my main problem. I'm looking for EVs within our electric usage. So how do we do this? So within most electric companies, you collect energy usage data on a 15-minute interval basis. And this is how we calculate the rates and calculate how much to charge you based on your usage. So most customers send us back this data so we can analyze it and look for patterns. So here's a sample of that. So I just made this up. This is a blue usage of some customer. So we're looking for true positives. What does EV charging look like? And so we asked some customers to let us monitor their usage. And so we basically put a meter in their house that is just for the EV charging. So it just monitors what EV charging looks like. And so we found it looks kind of like this. It's a sharp increase, pretty flat for a few hours. This is like 1 a.m. to 3 a.m. And then, nothing else. You're driving a car, just sitting in the garage right there. So you plot that you add that to the total usage. And so this is what we actually get from all customers, right? This is the data we get from all customers. We only have this data from like less than 200 customers. So we have that data. We also have some data from surveys. Customers answer surveys, tell us yes or no, they own an EV. So that's where we can get some more true positives, some more true negatives. And just to point out, this is all level 2 charging. So level 1 charging, like 120 volts, just a regular plug, that's not something we're typically interested in because it's not as, it doesn't consume as much energy so rapidly. So these are our true positives and true negatives. And so I have a question here. So this is time series data. Is this a time series or classification problem? So when you look at it, like the data is time series, but I'm doing classification. So I approach it as a classification problem. There might be ways of approaching it as a time series, but I approach it as a classification problem. And basically, I went about creating features from my time series data. So pulling, this is feature engineering, looking at data, looking for patterns as a human, not a computer, just looking for patterns in the data. What does charging look like? So most of the charging I found to be like this square-shaped curve, long duration and high amplitude. I wanted my features to be independent of time of day. I didn't want to limit when I expected customers to charge, even though I know most of them from surveys charge in the middle of the night, which is good for the electric company, but I wanted to find customers who didn't charge them too. Most charging lasts 2 to 6 hours. And then I was also interested in, I was worried about heating and cooling because that can sometimes look like EV charging. It's typically like an up and down cycle though. So I was trying to filter that out when I was building my features. So these are the features I came up with. I just used a simple random forest classifier as the first one I tried, gave me good results, I moved on. And so the features I found was basically I just counted the number of times the usage increased by some kilowatt hours and lasted for some certain amount of time and it happened during certain time periods. So just various combinations of these variables is how I define my features. And I just said, okay, count the number of times that happens. And then I also said, what's the average duration of this? Like for a customer in the winter, when it's 1 to 6 hours, what's the average duration? So those were my features. I'm just looking for things that go up and down. So these are the results. So the random classifier data, I took a whole year of data for those labeled customers. It's pretty good. It's like, wow, pretty good accuracy, precision recall, that's great. I'm happy with it. And just like moved on and said, okay, now. But then the business folk were like, can you validate this a little bit more than this your machine learning algorithm? So that was the next thing we did. So we do have some information about vehicle EV registrations within Washington State. It's provided at the census tract level, so we don't know like which address has an EV, but we know like this EV is in this census tract, which is I think smaller than a county size scale. So we know how many EVs there are in certain areas, and we know the Puget Sound PSC service territory, so we can do like a mapping overlap to try and count how many EVs we expect in our service territory. So when I applied my model to all of our customers in our data set, I found 80,000 EVs. It's like, okay, sure. And then I compared that to what the Department of Licensing came back. So I found there's actually, according to the DOL, 40,000 EVs within our service territory. So we're overestimating by twice, it seems. So what could be causing that? Because the model is like pretty good, but remember I'm training on like less than 2,000. So there's lots of things that could be going on there that I'm missing. So some possible reasons for the count discrepancy that we brainstormed was maybe the service territory and the DOL, we know they don't align exactly, but that's probably going to be a negative effect. It's going to be in the opposite direction. It's going to be even less EVs, so that's not helpful. Or maybe there's more than one EV per liter. Again, that's not helpful. Another thought is that maybe our model is finding EVs and also appliances that look like EVs. And that's kind of where the working assumption is what we're working on right now, and we're trying to explore that a little bit more. And so one way we tried to explore that is we went and surveyed our customers. And so the customers we surveyed were the customers who we predicted to be yes owners and not owners. So we said we surveyed those people who we thought would own and wouldn't own and see are we right. And so we got about 71% accuracy on that. And basically, so the recall is good. So we're finding most of the EVs that are out there. So we're pretty happy with that. But the precision is pretty bad. So again, we're finding things that aren't EVs. It's like, well, what are they? And it seems to match up with the DOL result too. So there's something there. And so one idea I had is like, well, maybe I just need to somehow get rid of these false positives. Can I explain away these false positives, right? These are the things I don't want. I want them to move over here. And that's because this idea of like, there's too many compared to this prediction. So how do I go about doing that? Is there something I can look at the data and try and figure where those false positives are coming from? And so I think so yeah, maybe it's something out else masquerading as an EV. So I looked at, in our survey, we also asked questions about appliances. What appliances do you own? And we found out, so I was comparing the false positives and the true negatives. Is the ratio of appliance ownership the same for these? Because if it is, then I can't explain it as a problem that appliances are showing up here. But I found out that my false positives have fewer gas furnaces than my true negatives. And what that means is that if you don't own a gas furnace, and you live in Washington State, then you probably have some other source of heat that's electric. So this is the electric. We think there's some electric appliance heating in there. There's lots of different types, so we couldn't really ask that question in the survey. And then another thing we found is that there's a lot more heated hot tubs for those folks. Like, well, there's another source of EV. So what happens if I remove these gas furnace owners and these heated hot tub owners from the whole sample? So not just from these ones, but from the whole sample. How does that improve my my performance metrics? So it gets better. So accuracy is 83. The most important one is the precision is not so bad. So we're doing a little bit better there. But there's still, there's still a lot of work to be done here because, this is, we still have to investigate this, I would say. But the question is, well, what's the right accuracy? Because your model came up with this, and then when you looked at the survey data, you got this, so what's right? So we think for the transformer upgrades, we're worried about things that look like EV. This is probably the right accuracy. Like this, yeah, maybe we're not finding an EV, but we're finding things that look like EVs, which are also bad, right? But if we want to market to EV owners, encourage them to charge in the middle of the night rather than midday, then we would have to upgrade our model to take into account that there's something else in there that looks like an EV. So it just depends on your use case, what you want. I mean, ultimately, we should probably improve the model, right? That's probably the next step, but in terms of current applications. So that's it for my talk. Just a summary. So PSC, we're doing our best to help customers, and one of the things we want to do is understand their EV charging patterns, who owns an EV, so we can make sure the grid is safe. Future steps, and I forgot to include that here, but basically improving the model, probably including those survey results in the model now, because we have more true positives, true negatives, so we can improve the model with these customers that look like things that aren't EVs. So that's it. Thanks, everyone.
Microphone, feel free to.
Yeah, my question is about, do you have to know anything about the EV owners? Like, are there EV owners that don't drive that far, so they would never meet your threshold of time? Or versus like, if they're EV owners that live further out, and so they would meet your threshold of time? Like, does that affect your goals?
So it affects the goals for depending on if you're a marketing person or an operations person, right? If you care about the grid, if they're not charging for long, they're not messing with the transformer, it's fine. But if you want to find, it depends on also your marketing goals. If you want people to convert at different times, if they're not charging very much, maybe you don't want to contact them. So it just depends on your business goals.
Tagging on to the first question, you were Puget Sound Energy. Can you not reach like Department of Licensing, get the license plates, 5,003,
So we have talked to them, and there's just privacy concerns. And at PSC, we also have very strict security concerns, like customer data. So it's not just they required us to sign certain security things, which we weren't comfortable signing, and so it's something we're constantly revisiting because we're both changing policies. So yeah, it's definitely something we want, but then once we have that, we don't need a model. So.
I just had an idea. I know your data set is already pretty small, but you mentioned about the heaters, and then maybe there's something to be said about getting seasonality and temperature. I know we just that's all the data.
Yeah. So we do have a model where we predict heating and cooling based off of daily data and temperature data. So that's another thing we could also incorporate is we do have that, we just haven't incorporated. So yeah, it's definitely something we want to do.
So this is such a good talk, this gets my brain going, and I want to solve this problem, so thank you. I am curious what your next steps in terms of improving the model are, because I think in the feature engineering, there's a lot of information that might be lost from you kind of filtering it out first. Are you planning to incorporate that in the time series ever, or what is the next step?
So I don't think we can incorporate the full-time survey because again, we have like 2,000 customers, and even with survey, so like maybe another 2,000. So I'd like to incorporate the survey responses. Also take a look at some of my features. Maybe they're not the best features, you know. I was just building the features off of this, what is it? Like this, the customers who said that they would give us the data from like their actual charging, and that's like 200 customers. So it's like not a lot. We do see patterns, like interesting things like Teslas and Nissan Leafs have different charging patterns. Like Nissans don't look like this. They actually have like an exponential decline, which is interesting. That I don't know if the models take that into account. Like I discovered it after the fact. It's like, oh, I wonder if we're finding those. So yeah, so lots of next steps.
Can you put census facts in the model? I wonder if it's
So yeah, so that's something my colleagues work on, is like including demographic data. So like, and that's more of a model to predict future like ownership. So we have models in PSC that use like demographic census data to predict how many EVs are there going to be in the future in this area. So I didn't like include like demographic data. I just wanted to be like based on the usage, what is it an EV? And it's mainly because it's coming from like the grid people. You know, they only thing they know is like usage. So like that's what they want to find is weird usage.
Yeah, I was wondering if like certain areas can have more electric heating than other areas, so that would, you know, kind of.
Oh, that might be something to think about. Yeah. Okay.
2 questions. First of all, I have an EV. How do I send to give you my data?
Oh, is it a level 2 charger?
It is, yeah.
Okay. Send me your address.
And then the second question is, I would imagine that this data set would be really interesting to a lot of other people. Have you thought about anonymizing it or figuring out a way to monetize it in some ways? Like companies are dying to get their hands on this for sure.
So I don't think there's a problem. Like PSE is like we're a private company, but we're regulated by the state. So like I can share all these. We don't have a competitor that would steal these results. So like I think yes, we could do it. It's just there's not really a lot of incentive on our part to do that. Like we don't really have like a research budget. We don't have like, you know, this is high tech data science at PSE. So there's not a big engineering group that helps us do that kind of thing. But it's definitely something we definitely be open to, I think.
I also have a 2-part question now, because these questions have been so good. Regarding that, have you done anything where you promote like, hey, we're trying to do this, if you guys have EVs, tell us, like that sort of,
So we do send out surveys, so this is stuff I'm learning about marketing, is like, we can't send those out a survey to every single customer asking them, do you own an EV? So we have to be like careful, we have to be conservative and just not flood our customers with all these surveys to get information. So yeah, we might have like a website where you could go to on your own and sign up for it. But, and we do have like an EV newsletter you can sign up, and maybe in there we can ask people to do it. But we can't like send an email to all customers saying, tell us if you're an EV. It's not, that's how marketing works, is what I understand. They don't like it when you do that.
and then I guess the second part, unrelated, you mentioned neighbors and having one person have an EV can increase the likelihood of others. I'm wondering how proximity works there, like how is an apartment complex being considered versus a home that has more acreage?
So, so in terms of like proximity, like for like the use case, it's if they're on the same transformer, that's what we care about. But more in general, like we're mostly concerned with single family homes because they're the majority, they're easiest to find, there's not this complicated who owns the EV, like is the EV this person and that person. So right now it's mostly single family homes and they're just the majority of customers.
We are at time. like you guys had such amazing questions and
Thank
if you want to connect with her after this meeting, or after this talk, then feel free to reach out right afterwards and also LinkedIn.
Yeah, sure.
So Andrea Urban on